Folks, this is where we ended up, and we had this example problem, like usual, and the example problem says, hey, you're going to take these molecules and you're going to react it with sodium borohydride. What is the product from the reaction? And we're supposed to go through and be able to draw a structure from the name. Well, yeah, that was part of the IUPAC nomenclature system that we talked about in the beginning of this lecture module for aldehydes and ketones. It is just a reconfirmation step. That's all that it is. So we have to go from the name to the structure. Once we get the structure, we react with the reagent sodium borohydride in order to predict a product. All right, so let's kind of start with the first one, 2-methyl propanol. Okay, so prop is a 3-carbon, a 1 and a 2 and a 3. Now, propanol has an AL ending. AL ending means aldehyde, and there's the aldehyde functional group. So propanol, there is the aldehyde group, C double bond O with a hydrogen and 2-methyl. All right, so carbon 1, carbon 2, we have a methyl group on our structure. All right, so 2-methyl propanol. There you go, folks. And we need to react this with sodium borohydride. So NaBH4. Okay, so if these reactions go forward, what on earth is going to happen? You know what's going to happen because we've learned the mechanism over and over and over and over and over and over and over. We know exactly what will go on here because sodium borohydride, we just learned, is our nucleophile. The nucleophile is a hydrogen in this case. And guess what, folks? The hydrogen goes and it does what the hydrogen always does, or a nucleophile always does. Well, we can draw the curvy arrow if we want. So the nucleophile sees the partial positive carbon of the carbonyl, and carbon shoves those electrons up to the oxygen. The oxygen tries to shove them back, and carbon says, oh, no, I don't think so. I don't have a leaving group. Sorry, oxygen. So I'm going to redraw 1, 2, 3, carbon, double bond O, and the hydrogen. I'm going to redraw the structure, and then we're going to break the double bond, and what we have is a hydrogen that was new. This was my incoming nucleophile, and a negative O that has formed. All right, now, we could go another step, and we could go ahead and say, well, you know what, we know. This negative is not going to stay behind. We can protonate it by the form of some type of acid. And there you go. There's your product for the reaction scheme. All right. So what I've done is that I've drawn the reagents. I've drawn the mechanism out. That's the curvy red arrows that you see on your screen. And that is our product that has been formed from this reaction, folks. All right. So there you go. One fell swoop. And that's all that we need to do. Now, we could, if we wanted, name the product because we know how to name that product. It's an alcohol. We should know how to name alcohols at this point. If you don't, shame on you. So let's go through and name it. All right, so the longest carbon chain here is a 1, 2, and a 3, no matter which way you go with it. So this is a propane. Drop the E and add OL for propanol. Well, that propanol is going to be carbon number 1, carbon number 2, carbon number 3, because it's at the very end. So this is a 1-propanol. I could leave that 1 off if I wanted. And then at carbon number 2, folks, we have a carbon that's hanging off. And I've not named that one yet. So at carbon number 2, we have a methyl group. So 2-methyl, 1-propanol is going to be the product from that reaction. If I wanted to name the reagents, well, the question kind of did that for us, but let's do just a quick review, a confirmation on how they got that name. 1, 2, 3. All right, so there is a 3, which is a propane. Drop the E, add Al because it's an aldehyde. At carbon 1, and at carbon 2, and at carbon 3. At carbon number 2, I have a methyl group. So 2-methyl propanol reacts with sodium borohydride in a nucleophilic acyl addition reaction, breaking the double bond of the carbonyl group, forming 2-methyl 1-propanol as a product, where hydrogen from the sodium borohydride is acting as the nucleophile. Folks, there you go. There's the magic of organic. That was a foreign language to someone that's not taken organic yet, but it wasn't a foreign language to you because you're learning. That's the key. You're learning, and that's really all that matters. So 2-methyl propanol makes 2-methyl 1-propanol in the presence of sodium borohydride. Okay, so let's talk about the other example. Number 2. Number 2 says cyclohexanone. All right, so cyclohex is a cyclic ring with 6 carbons. And one is a ketone, so I'll just draw it up there at the top. It's pretty that way. All right, so cyclohexanone is going to react with sodium borohydride. And there we go. Well, I'm not going to draw the mechanism this time. I'm just going to draw the product that gets formed. So here is what we started with. I know that this is a hydrogen nucleophile, and we're going to the double bond. And what we do is we add on a hydrogen at that spot, and that creates a negative at that oxygen. And then we can go through and protonate this if we want to with the presence of some type of acid. We know eventually it's probably going to happen. So I'm just going to assume that we just need to go ahead and do a hydrogen there as well. All right, so that will protonate the negative oxygen that is present. So there is our example problem, and there is the product. Now, hydrogens and carbons we tend to leave off, right? These are skeletal structures. So this hydrogen I've drawn here just to let you know that we did add something to destroy that double bond, and that nucleophile was a hydrogen. So if I wanted to, I could just simply get rid of that hydrogen. There's no need to write it. We've not written any of the other hydrogens on the molecule. Why that one? So sometimes they'll leave that off, and this would be a much cleaner kind of representation of the reaction. So this is cyclohexanone. It has reacted with sodium borohydride in a nucleophilic addition reaction. We have destroyed the double bond of the carbonyl group, and that has formed an alcohol as a product. What is the name of this alcohol? Well, this is cyclohexane, and add OL for cyclohexanol, folks. That's what we do. So there is the reaction. There is the answer to that reaction and to the example problem. All right, now finally, we have our third one, and our third one started with benzaldehyde. Do you remember the structure for benzaldehyde? I hope you do, because we went back and we kind of talked about that in the benzene lecture modules. So once again, I'm going through and I'm wrapping up just different types of topics and ideas that we have talked about over the course of the semester. And there is benzaldehyde. And now you know why it's called aldehyde, because the C double bond OH group, aldehyde, there you go. And benz, because that's the benzene ring. This is a common name. It's not the IUPAC name, folks. The IUPAC name is something different. But this is the common name for that structure back in the day when we were studying benzene reactions. All right. So here is our benzene group with our C double bond OH, so benzaldehyde. Benzaldehyde reacts with sodium borohydride, and we have a product that gets formed that is an aldehyde. It is a type 2 carbonyl. Type 2 carbonyls break the double bond, but a leaving group does not go away. So here is my starting reagent. That's kind of where I like to start each and every time. And then I'm going to the double bond. There we go. And a hydrogen has been added onto that carbon now from the sodium borohydride piece. And that created a negative oxygen. That negative oxygen is not going to stay around. We're probably incorporating acid in some form or some fashion. And when we do, that turns into a OH group. So folks, there you go. There's the product for that reaction. Okay, something else that I would like to say here. We've never really kind of termed these reactions, and back in general chemistry, you probably had an onslaught of things that were called redox reactions. And redox reactions was this whole concept that you can lose electrons or you can gain electrons in reaction schemes, okay? And this was a way that we went through and kind of classified, especially half reactions back in the day. So when we were talking about galvanic cells and batteries and how they work, all of that is based off of redox, as well as a few other reactions that we can do in a laboratory as well. So you might have been introduced to Leo goes grrr. Okay, so Leo the lion growls, right? I mean, that's what this kind of is. Leo goes grrr. Okay, so Leo is loss of electrons. That's what that stands for, loss of electrons, and grr is gain of electrons. So the O is going to stand for oxidation, and the R is going to stand for reduction. So loss of electrons is oxidation, gaining of electrons is reduction. The reason that I say this is because I'm kind of giving, credit where credit's due. And sometimes that credit needs to be given in the general chemistry field. That's great. All right. That's perfect. However, you also need to know that redox can also happen in organic. And when redox happens in organic, we look at this and we define it a little bit differently. And we look at the number of carbon, and in this case, oxygen bonds. So in organic chemistry, we can talk about redox. We can actually give you a description that's very similar. So loss of electrons and gain of electrons, we can go through this whole kind of definition game if we want to, but we're going to define it a little bit differently in organic, and we can talk about reduction reactions, and we can talk about oxidation reactions. And in reduction reactions, what do you think reduction means? Reduction means to reduce. So in a reduction reaction, we are reducing the number of something like carbon to oxygen bonds. So in the sodium borohydride field, what I need you to understand is that these reactions are reduction reactions. So that's just an extra little word that we can throw off, because look at what we're doing to the number of carbon to oxygen bonds. We are reducing them, aren't we? So we are taking carbon, and it did have a double bond to an O, and we are ending up with a carbon, a single bond to an O. So we are reducing the number of carbon to oxygen bonds. So we can start to classify reactions in organic chemistry this way. So I don't really talk about this a lot, because I think that redox in terms of general chemistry is a little bit more applicable in this case in a real laboratory environment or in a real world type of scenario. But these definitions do follow through in organic chemistry as well. All right. Okay, so let's talk about another type of reaction now. We kind of done all that we need to do with sodium borohydride, and this is the hydrogen nucleophile that's get it on. So let's take a look at now type 2 reactions with something like HCN. This is just another example I'm going to go through. I don't think anything that I'm getting ready to say will be surprising to you at this point, but I just kind of want to do it for formality reasons. So hydrogen cyanide, that's what this basically is called. Hydrogen, because the hydrogen in front, and cyanide, because we have a CN bond here at the end. So cyanide, there we go, cyanide. This also can go by a different name. This is a carbon triple bond N, and this piece carbon triple bond N is the nitrile group that we have talked about before, especially in infrared spectroscopy. So nitrile or cyanide, it doesn't really matter which one you want to use. I don't really care. A lot of people like to use cyanide because it sounds very deadly and, poisonous and like it can kill people and they think it's cool. But other words, nitrile seems a little safer, but we're really talking about the same type of thing here. So the products that happen from these reactions are going to be called a cyanohydrin because of that, and you'll see that in just a second when we begin to start forming some of these products from these reactions. So HCN, I will say, this is very dangerous. We do not want any of these containers out in our laboratory. It can kill people, folks. So HCN, we kind of want to use as we need it, and we kind of want to generate it when we need to use it for that particular moment. So I don't ever really want a container of something like hydrogen cyanide around. It's not going to work out for me. It's not going to be very stable. It's going to be very poisonous. It's going to be hard to handle, especially with untrained people. So we can generate this stuff if we use hydrochloric acid, which is something that is kept around in a laboratory almost all the time, and sodium cyanide, NaCN. So this is also a pretty shelf stable compared to the HCN component that we can order for a laboratory and that we have more control over its use. So if I take the NaCN, and this is an ionic compound, right? Because sodium is a positive and cyanide is a negative. So this is an ionic compound. It's probably something like a salt. And I add that salt to HCl and I give it a good mix, I will begin to generate HCN that could be used for the organic reaction scheme. So once I form the HCN, folks, I need you to understand that it's still a nucleophile. The nucleophile still does the same thing that type 2 reactions actually do. All right, so let's take a look at what goes on, and we'll begin to look at the power of HCN, because, folks, this is also an acid, right? I can see it's an acid. There's a hydrogen right there in front. That's the basic general chemistry definition. So let's take a ketone, a C double bond O with a CH3 on the left and a CH3 on the right. That's acetone, okay? So I'm going to take acetone and I'm going to react this with the nitrile group. What product's going to form? Well, I shouldn't have to lead you through this mechanism, because you're going to look at this and say, oh, well, Tracy, I know exactly what to do. This is a nucleophile, and this is a type 2 carbonyl, because you taught me that. And this nucleophile will go in and attack that carbon, bing, and that double bond breaks, and then we see this oxygen try to shove those electrons back onto that carbon, and carbon says, no way, no how. I'm not going to fall for that trick again, oxygen. And when that happens, we see a double bond that gets destroyed. All right, so I'm just going to redraw our starting reagent. There we go. And then I'm going to that double bond, and we have a C triple bond N that shows up onto that carbon. Now, we also have this oxygen that is negative, that is present, all right? So that oxygen, it needs to be satisfied. It needs a proton, folks. And because it needs a proton, guess what? We are using HCN. So it also gives us the H that we need for that oxygen to become satisfied. There we go. So, folks, there's your product from the reaction. HCN plays double duty. HCN gives me the nucleophile that goes on to the acyl carbon, and the hydrogen is the proton that goes on to the negative oxygen when it forms. Okay, now I told you that these products are called cyanohydrins, and the reason is because cyano represents the C triple bond N. There is the cyano part. And then the hydrin is in reference to the OH that is here. So we can call this actually acetone cyanohydrin. If we want to name it and give it something like a common name, that's how we can do that. We call it acetone because that's what its precursor was, and cyanohydrin because the C triple bond N and that OH is both on the same carbon, and both components are there, and it came from HCN, and that is the proper kind of name for that particular functional group. All right, so that's the only story that I need to tell you with the cyanides or the nitriles that will come along in these reactions. You treat them just like before. You treat them just like a regular old nucleophile. We just have a special name that gets associated with them. So the next functional group that we're going to talk about with the type 2 reactions will be the functional group of NH2. Oh, I remember NH2. That was Miss America from the nucleophile chart. Yeah, that's right. We said that this was really the powerhouse of the nucleophiles. That if a NH2 came onto the molecule, it was going to be very hard to get rid of that NH2 because that is Miss America and that is no way ugly for a leaving group. So the carbon is going to latch on to the NH2s whenever they can happen, and it will keep those NH2s under all circumstances, at least most of the circumstances that we will see in General Chemistry 1 and 2. So let me kind of give you a rundown of how these are going to behave in the world of type 2 carbonyls. So let's say that we have an aldehyde or a ketone. I'm just going to draw a C double bond O, and then on this side a CH3, and then on this side let's do a CH3 as well. We'll keep it as an acetone, very simple. This would also work if that was a hydrogen and an aldehyde. Either one. Okay, we're still talking about type 2 folks, and those are the type 2 functional groups. So we are going to react this with some type of amine, and that amine is going to probably have some type of alkyl group that's coming around with it, right? We just can't have NH2 in a jar. So NH2 negative is not a bottle of stuff that I can pull from the shelf. I've got to get it from somewhere. So this piece is going to be some type of alkyl component, and it could be a carbon chain, 1 carbon, 2 carbon, 3 carbon, 4 carbon. I don't care. It doesn't really matter. So here's type 2, which is a ketone, and we are reacting this with a amine. Now, keep in mind, this is not an amide. That is not an amide. An amide is a carbon double bond O to a nitrogen-containing group. We do not have a carbon double O attached to the nitrogen in that reagent, do we? No, it's just a simple little low carbon chain. So this is a amine, not an amide. So the amine will react with an aldehyde or a ketone, and it will produce a product. So what kind of product is it going to produce? Well, let's kind of use the rules and see if we're right. Oh, Tracy, you told us this NH2 is a nucleophile, so this NH2 will come in and it will that particular type of carbon, and that makes that carbon double bond O break, and then that piece will be shoved up to the oxygen. There's no really good leaving group, so maybe what we have here is a carbon double bond O in the beginning, and then the double bond breaks, and we see a NH2 that gets added on, and then this oxygen is negative. Okay, well, I wish that it was that easy. I wish that this followed the same reaction scheme that some of the others do, but quite honestly, folks, it does not. That is the problem with the amines in the type 2 carbonyl reaction scheme. So what we end up with here is not correct. If this is a structure that we have drawn, mechanism-wise, this is kind of what we've always done, right? So while on earth would we not end up with something that looks like that? Well, what we end up with instead is a carbon double bond O. I'm going to start off with my starting reagent like I do most of the time. And what happens here is that this primary amine, that's what this is, right? It's a nitrogen that's attached to one carbon, and it's only that one carbon group that it's attached to. So that's a primary amine. So this primary amine has an alkyl group and a nitrogen that is there. And it also has these two other hydrogens associated with it as well. Well, if the NH2 goes on the way that it does here, this is a very strong base. That very strong base goes in to that carbon, and this carbon gets kind of overwhelmed. I mean, this beautiful NH2 has come in, and it's taken maybe an interest in little old me, and that carbon is just really infatuated with that NH2 group. And that oxygen has the electrons at this point. But folks, here's the problem. This is not an acid. I know I could add acid a little bit later on, but this is going to form a O-. And this O- is very negative, of course, right? And this NH2 is one of the best bases that are out there. So I need you to think of this as a very negative component too. And when two very negative components come onto the same carbon, then they are going to fight, they're going to scratch, they are going to hit each other, kick each other, punch, scream, whatever they decide to do to each other. Carbon is just blindfolded to it and says, just don't bring me into the middle of it. I'm in the middle of this love triangle, but don't bring me into the middle of it. So these two negative pieces are not going to get along on that carbon. So one got to go, folks. One of these has to go. So instead, what happens with the amine to make this molecule very happy? Well, we are going to, but we're going to the oxygen instead. So nitrogen comes in and basically bullies the carbon off of that molecule, or the oxygen off of that molecule. That nitrogen comes in, it slips a note and it says, this is my man, or this is my woman. You're going to leave carbon alone. And my advice to you, oxygen, is you pack your bags and you get it. Get out of here. And that oxygen, and away it goes. So we open up now room for the nitrogen to take the place of the oxygen. It is so strong. It's such a good nucleophile that this is why it behaves differently. So that nitrogen goes on in the place of that oxygen. Notice I didn't do anything to the double bond. The double bond actually didn't even break. The nitrogen just takes the spot of where the oxygen is located. Now, with that, though, remember, nitrogen has to have 3 bonds. 3 bonds, that was chemistry 251, formal charge of 0. 3 bonds and 2 electron dots. Okay, well, it's got the electron dots. It's right there. I've just not drawn them. But the 3rd bond is going to come from the alkyl group that was there in the beginning before all of this ever happened. So what we form is a product, and this product has a functional group, and this functional group is a new functional group that you have not been introduced yet. And this carbon double bond in to an R is called an amine. I-M-I-N-E, because I mean, he's so mean that he's going to replace oxygen and tell it to go away. That's an amine. So an amine is going to be formed as a product, and that is the functional group for this particular piece. A carbon double bond to a nitrogen with one other maybe carbon attachment to the nitrogen at that point. We actually have a special term that we use for this particular type of structure or functional group, And this is also called a Schiff base. A Schiff base. So if I want to call it an amine, that's great. If I wanted to call it a Schiff base, I can do that as well. So just some more terminology to add to our belt of the already growing organic chemistry nomenclature. All right, now, this was an aldehyde, a ketone, that reacted with a primary amine. Okay, so now what I want to do before I stop this video is I'm going to take the same molecule that we started with before, acetone, and this time we are going to react it with a nitrogen-containing nucleophile, an amine, but this time it's attached to 2 alkyl groups, not 1. So this is a secondary amine. It's secondary because it's attached to 2 carbon pieces. So one of the hydrogens have been replaced. That hydrogen has been replaced with another carbon chain. It could just be 1 carbon. It could be 10 carbons. I don't care. It's just our R group, random alkyl group. And this works kind of the same, but kind of it doesn't. Oh gosh, what does that even mean? Well, the same kind of scenario happens here, and the scenario is nitrogen comes in and says, amine, and it kind of kicks off that oxygen. They don't get along. They never have. They never will. And nitrogen comes on, and it takes the spot of the oxygen instead. But it doesn't happen quite as neatly as the formation of the amine does. Something happens here, and the reason that this goes on is because this secondary amine, I need you to think of it as being a little bit bulkier. There's a little more thing that it's bringing to the table other than nitrogen and maybe 1 carbon piece. It's now nitrogen and 2 carbon pieces. So the problem that we have here is room. And we start to see a rearrangement that begins to happen in the molecule. So what goes on if I form the product here? I'm going to start off with my reagent of acetone that's there. And if you go by the primary amine, you would think, oh, well, this oxygen kind of goes away right there. And this nitrogen will replace it. And this nitrogen will bring an R group to the table and the other R group to the table, right? I mean, that's what we did in the very last example. We said nitrogen brings in the R group, and in this case, it brings in the R groups. There's just 2 of them now instead of 1, right? And the answer is no. This is where the problem happens. Because what did I just tell you a couple of minutes ago? I told you that formal charges for nitrogen want 3 bonds and 1 set of electrons, didn't I? Well, take a look at what you just did. You have now created 4 bonds for nitrogen, and that nitrogen has 4 bonds, and that is going to give it a positive charge, and that will not stay around on the molecule. So we have a problem, Houston, and we need to get rid of that that positive charge that's there, meaning we have to get a set of negative electrons. So what happens here is a rearrangement will begin to take place. So this nitrogen does go on to that double bond O, okay? Think of this as the very first step, very similar to the formation of the amine. And then this nitrogen brings with it the R groups. There's just so happen to be 2 of them and not 1 of them. And that's exactly what the amine did that we talked about just a few minutes ago. But the problem here is that there's now too many bonds. So this nitrogen says, listen, carbon, if you want this to work, you're going to have to rearrange something. You're going to have to quit everything that you do to make me happy. Do you know somebody like that? Well, that's nitrogen. And nitrogen's going to come in, and carbon's going to say, okay, like he does every single time, okay? So this double bond will break. It will no longer be between the nitrogen and the carbon, and you can kind of see why. Because now this frees up that nitrogen to have 3 bonds, and that's exactly what we need from that. We need 3 bonds. So that set of electrons has to go somewhere, folks. It has to go somewhere. And that double bond will shift, and it will shift inward toward one of the other carbons that are there. Now, in order for that to work, we're going to have to get rid of a hydrogen too to make a spot for it. So this molecule will rearrange the double bond. It shoves it inward, and it gets rid of a hydrogen. So that way it can have room for that double bond just to make the nitrogen happy. All right. So what goes on here is that we have the oxygen that was kicked off from the carbonyl. We have a hydrogen here in the secondary amine that was not used. So that hydrogen's out there. And now we just have a release of another hydrogen from the molecule. So that way that double bond could form. And that's our second hydrogen. So what's HOH? Well, it generates water as a product from this reaction. So we can take a type 2 carbonyl and we can react it with a secondary amine. Now that's the kicker. It's a secondary amine in order to make this type of functional group. And this type of functional group, this nitrogen that is on a carbon with a double bond, is called an N-amine because I have shoved the double bond inward into the molecule. So because I shoved the double bond inward, and because I used an amine to make it happen, we're going to call this an N-amine. And that is going to be the functional group terminology that we use for that particular product. All right. So this is an N-amine functional group. So a type 2 carbonyl reacts with a secondary amine to make an N-amine as a product, not an enemy. That's something different. Maybe organic chemistry is your enemy. I don't know, but it's not an N-amine, and it's not an enema either. All right. And then that N-amine will also come along a water molecule, because we're losing the oxygen of the carbonyl and 2 hydrogens throughout this process. All right. So just to sum it up, a primary amine reaction with a type 2 forms an amine functional group, and that is a carbon double bond nitrogen with a random alkyl group. That was okay. There were still just 3 bonds. A secondary amine is a little different. The secondary amine will bring both of those carbon chains to the table, and because of that, we need to free up a space. We shove the double bond inward to the molecule, and we call this an N-amine because we shoved it inward. So there is your amine reactions for a type 2 carbonyl. All right. Okay, so that's where I'll stop this video. In the next video, we'll pick up from here, and we'll continue on talking about reactions.